Welcome to Discovering Geometry. My name is Becky Berry, and this is Lesson 4. So when we are making definitions in geometry, we need to make them well. A sloppy definition leaves room for your imagination, and different mathematicians may be having different ideas of what something is. Let's look at this picture. We have widgets. We have a picture where we have all widgets and a picture where none of these are widgets. Let's use these pictures to make a definition. What do we see that all these widgets have in common? I see that they're closed shapes with solid colors inside, and they have things coming off the side of them. What things do they have? They each seem to have one eyeball, and they each seem to have one claw. It looks like maybe exactly one eyeball and exactly one claw. This over here is a solid closed shape, solid color, but it has two claws, no eyeballs. This one has a claw and an eyeball, but there's no color inside. So that may be why this one isn't. Here is a shape. It's got a color inside, it's closed, it's got an eyeball and a claw, but it has something else inside of the shape. So do we need to change our definition to say that it can only be a solid color inside? And this one, this last one, is a triangle shape and it has two claws. So I think a definition with one claw and one eyeball exactly is what we should be thinking of. So again, what would our definition be? Possibly that they all have colorful bodies with nothing else inside, two tails, one with a claw and one with an eye. So now that we know what our definition of a widget is, which of these are widgets? Based on our definition, B has two claws, so that's not it. D has three claws and no eyeball, so that's not it. C has one claw and one eyeball, but something else inside. A has one claw, one eyeball, and nothing but color inside. So A is our only widget. Let's think about good definitions and how to make them. Our definition of a protractor was a geometry tool used to measure angles. So we classified it right here, a geometry tool. That's how we classified it. And then how is it different than other geometry tools? Because a compass is going to be a geometry tool. A straight edge will be a geometry tool. How is a protractor different? Well, what is it used for? It's used to measure angles. So when we're writing a definition, we want to classify it, and then we want to tell how it's different. And sometimes we may even have to have 2 or 3 parts to how it is different from other things that are classified in that group. So what is a square? When we write our definition, we need to classify it, and then we need to tell how it is different. And again, we may need more than one point here. So what is a square? You might say it's a quadrilateral. You might not use the term quadrilateral. You might say that it's a four-sided polygon or even just a four-sided figure. So then how is a square different from other four-sided figures? Are you saying that all the sides are the same length? Okay, let's try out that definition. Which one of these, or which of these are squares? I think we know just by looking that this is the only square. So this is a four-sided figure, but the sides aren't the same length. This is a four-sided figure, but the sides aren't the same length. This one's a four-sided figure, and it looks like the sides are the same length. Why is it not a square? Maybe we should add to our definition that it needs to have 4 right angles. So a square is a figure with 4 equal sides and 4 right angles. You may define that a little differently and say that a square is a 4-sided figure that has all sides congruent and all angles measuring 90 degrees. So your definition can be a little bit different, but you need to make sure that you have things in there that will differentiate it from all other 4-sided figures and that will classify it as to what we started with. If we just say a square has all equal sides and all right angles, we might draw something a little crazy that's not quite a 4-sided figure. Let's look at parallel and perpendicular lines. Here is a picture of parallel lines. What could our definition be for parallel lines? Well, let's classify it. They're lines, and in this case, they're in the same plane. Lines in the same plane, and then will they ever touch? They will never cross. So you could say lines in the same plane that never cross. You could maybe say lines in the same plane that never meet. What about perpendicular lines? Well, these lines cross one time and they form right angles. So perpendicular lines are lines that meet at 90-degree angles. Or you could say perpendicular lines meet at right angles, since we know that right angles are 90 degrees. Now, why did we use lines in the same plane that never meet for parallel lines, but we didn't specify that perpendicular lines had to be in the same plane? Is there a possibility of having lines that are not in the same plane and they never meet? What if this is our plane? Imagine that's a piece of paper and I draw this line on it, but then I draw a line coming out of it straight up that's going to go down underneath it. Will these two lines ever meet? But are they parallel? So we have to specify that parallel lines are in the same plane and they never meet, because we could have two lines in different planes that also never meet. These would be skew lines, not parallel. Let's write some more definitions. How about right angles? What do you notice about all of these that is not true in these over here? Hopefully you're seeing this little symbol in the corner. That means it's a right angle, and this gives us what a right angle is. It's 90 degrees. This one we have two perpendicular lines, and we said that two perpendicular lines cross at 90 degrees. So all right angles measure exactly 90 degrees, not more and not less. So that's a pretty simple definition. A right angle is an angle that measures exactly 90 degrees. What about acute angles? Here we have some acute angles. Well, this one looks really close to a right angle, but it's labeled for us. And here we have angles that are not acute. We even have a 90-degree right angle right here. So what's our definition for acute angles? Hopefully you're saying an angle that measures less than 90 degrees. This one might even be 89.99 degrees, but that's still less than 90 degrees. Obtuse angles. Can you figure out what a definition is for obtuse angles? These are not, and these are. You might be saying angles that measure more than 90 degrees. But could we even say that they measure less than 180? Is that needed based on our definition of an angle that we had in a previous lesson? It may not be. If we defined angles as the smallest measure, then if it was more than 180 degrees, if we started measuring this angle, it'd be more than 180, but the angle as we defined it was the smaller measure between the two rays. So I think that we could safely say that obtuse angles are angles that measure more than 90 degrees. I will say that other geometry courses do not put that definition in for an angle, that it's the shortest or the smallest measure. And so obtuse angles do have to be between 90 and 180. But in this course, we've already defined an angle as the smaller measure between the two rays. So you can't get bigger than 180 in that case. What about pairs of vertical angles? This is maybe one you haven't heard before, so let's take a good look. I'm just going to draw in here. So this is angle 1, and this is angle 2. What do we notice about 1 and 2 based on all of these angles between these lines? And then we have angle 3 and angle 4. Here we have AED, so this one here, and BEC, this one here. We also have AEC, pull out a different color to show that one, AEC and DEB. All right, so now we've defined the red ones as vertical angle pairs and these blue circles as vertical angle pairs, but not all of them. So these are not vertical angles. 1 and 2 are not vertical angles. In this case, 3 and 4, well, they come off of 3 different lines, so I can maybe see that. 5 and 6, not vertical angles, but they're kind of across from each other. 7 and 8, also not vertical angles. And 9 and 10, oh, I see they're not touching, so they're not vertical angles. What would your definition of vertical angles be? I might say that vertical angles are opposite angles formed by the intersection of 2 lines, not 3 lines, so 3 lines would be here, not touching, so these aren't lines that are together. And here, 5 and 6, this isn't a line because these are 2 rays. They don't measure 180, so that's not one line. And then 7 and 8, it would actually be 3, that these rays here aren't the same. So again, my definition was opposite angles formed by the intersection of exactly 2 lines. How about linear pairs of angles? Let's look. 1 and 2 are linear pairs. 3 and 4 are linear pairs. AED with AEC and BED with DEA. These are not linear pairs. 1 and 2, well, they're next to each other. 5 and 6 also next to each other, but what's the difference between 1 and 2 and 5 and 6 over here versus 1 and 2 and 3 and 4? And then 3 and 4 right here, A and B, well, A and B add up to 180, but they're not together. So what might our definition of a linear pair of angles be? It might be 2 angles that together make up a full line. So we have a line here, and 1 and 2 are the 2 angles that make up that line. 3 and 4 are the two angles that make up this line. And then again, AED and BED, they make up this line. So two angles that together add up to one line. Or maybe two angles on the same line, or that form the full line, however you want to write your definition. Pairs of complementary angles. Oh, right here it says the measure of angle 1 plus the measure of angle 2 equals 90 degrees. So complementary angles include 1 and 2 and 3 and 4. What do you think 3 and 4 add up to? Hopefully things that you are noticing. A full line is 180 degrees. This is a right angle, which we defined as 90 degrees. If the full line is 180 on this side, then the full line over here must also be 180. If we take out this 90 from this right angle, what's left for angle 3 and 4 to be? Well, 3 and 4 must also add up to 90. What about over here? What are not complementary angles? Well, G and H are 40 and 52. They're not complementary. 3 and 4, they're next to each other, but it looks like they're a linear pair. What would they add up to together? 3 and 4 would be 180 degrees. And then 1 and 2, they look pretty small, and it even says up here, the measure of 1 plus measure of angle 2 is not 90 degrees. So complementary angles, what's your definition? How about any two angles whose measures add up to 90 degrees? Let's look at our last one, supplementary angles. We have 3 and 4, the measure of angle 3 plus the measure of angle 4 equals 180 degrees. And we see that 1 and 2 are on the same line. So 1 and 2 are supplementary, and 3 and 4 are supplementary. So 1 and 2 are linear pairs, but 3 and 4 are not because they're not on the same line. But we know that their measures add up to 180 degrees. About 4 and 5, the measure of 4 plus the measure of 5 is bigger than 180. So 4 and 5 together is going to be more than 180. And then 1, 2, and 3, that's 3 angles. But they add up, they're a linear, they add up to this line. So looking at these two, what is our definition of supplementary angles? I would say that it's two angles that add up to exactly 180 degrees. We see that it can't be 3 angles that add up to 180, and they can't add up to something else. So 2 angles that add up to 180 degrees. Things to note. Your book has no glossary. So as you're making these definitions, pulling them out of our notes, out of our lessons, out of the book in the lesson that you read, you need to be keeping track of them. I would suggest using maybe another notebook, or maybe you have a binder where you want one section to be your definitions, and transfer them all over. At the very least, you could take a highlighter and highlight each of the definitions the first time we use them in your notes. Speaking of your notes, you need to stay organized in order to succeed. Make sure that you are hole punching your notes, keeping them all together. I suggest a big binder. You could have one tab for your notes, one for your definitions, and a third tab even for your homework. Keep up with all of it. So, do you have your binder yet?